Hello and welcome to today's class. Today we're going to be looking at the theories of elastic failure. So we're going to be looking at when we would consider a material likely to fail because the material has exceeded the yield point. We're not considering other failure modes such as buckling and so on. We're simply looking at the failure of the material. Okay, so we're going to be looking at different theories that are out there. We're going to be discussing which theories you should be using and how you would calculate the failure theories predicted or the failure stresses predicted by those theories. We'll have a look at the theory. We will then move on and we'll have a look at some examples. When we look at those examples will be drawing upon some of the previous theories that we've used in class, such as thin cylinder theory, simple theory of elastic bending, complex stress theory, and so on. So I'll go through the examples and I'll discuss where we're using those. So you may need to go back and refresh yourself on some of those theories if you're not completely confident with those. Okay, so that's what today's class is all about, the theories of elastic failure. Okay, so the theories of elastic failure. So if you're looking at, I don't know, some finite element analysis or something like that, you may well see some screenshots like this. Okay, here's a component, a crank or something. You can see we're showing the maximum principal stresses. So we would see our images like that. So what I want to do today is discuss our maximum principal stresses. We know how to calculate our maximum principal stresses from our complex stress theory. Okay, so we've shown our maximum principal stresses and we've shown how we can calculate our maximum principal stresses from the stresses which are set up in the system which we're assessing. So we know stress is force over area. We know how to calculate our basic stresses, our one-dimensional stress. We then take those stresses and calculate stresses in 2 dimensions or 3 dimensions and calculate our principal stresses and our maximum principal stresses, sigma 1, sigma 2. You can see we're plotting that in this image here. Okay, so we understand how to get to our maximum principal stresses. So that's what this piece of software here is showing, our maximum principal stresses for this component being loaded in this situation. These bottom images now, rather than showing our maximum principal stresses, are showing something called our von Mises stress. Okay, most FE solvers at the moment will default to showing you your von Mises stress. So when you plot stress, and what you're actually looking at are your von Mises stresses, which is what we're seeing in this image here. Here's a component, I don't know what that component is, being loaded in some way, and we're plotting our von Mises stress. So somehow we've gone from our maximum principal stresses to our von Mises stress. Most FE solvers, you can actually decide what stress you want to show, whether that be maximum principal stress or von Mises stress or whatever. There are other versions as well, other types of stresses which you can also plot. But by default, most FE solvers at the moment will show you your von Mises stress. So how do we get from our principal stresses? We understand about our principal stresses from our complex stress theory. How do we get from our principal stresses to something like this, our von Mises stress? Okay, notice our principal stresses are positive and negative. Our von Mises stress are all positive. Okay, and there's a reason for that. The von Mises stress is just a weighted average of our principal stresses, and essentially we take our principal stresses and we square them all. So that's why our von Mises stresses are all positive, because we've taken our principal stresses and we've squared them. So what I want to do in today's class is discuss how we would calculate our von Mises stress, or a different type of failure theory, how we would calculate that failure theory from our principal stresses. Okay, so what are the theories of elastic failure all about? So we've seen before how you can do a simple tensile test with a small piece of material. So you're loading it in one direction, and you can work out what is the maximum stress that that can take before it starts to yield, before you start to see this plastic deformation. From that, we can calculate a number, the yield stress of that material in that load condition. So this is what I'm talking about here. So we're doing a simple tensile test. We've got a specimen that looks something like this. We're doing a tensile load on that. So we're pulling it in this direction vertically, and we can plot stress against strain. Initially, it's elastic, and then it starts to yield, and then we see this plastic deformation here. Okay, so up until point A, it's elastic, and we're considering the yield stress at point C here. Okay, so the yield stress for this particular material in this particular one-dimensional load condition is given by this number here. Okay, the yield stress of this material. Okay, so what our complex stress theory then says is, well, rather than loading it in one dimension, and we've looked at this before, rather than loading it in one dimension, let's load it in 2 dimensions, or actually in real life, you're loading it in 3 dimensions. But we said, let's simplify that when we were looking at complex stress theory. And we said, instead of loading it in one direction, let's load it in 2 directions. And we worked out what the stress was internally within the material on any plane. And we said, well, actually, when we're designing a component, it's not the stress at any plane which we're interested in. We're interested in the principal stress, the maximum stress, and we came up with this equation here. Okay, sorry, we came up with this equation here, sigma 1, 2. So sigma 1 being our maximum principal stress, sigma 2 being our minimum principal stress, is a half times by sigma x plus sigma y. So that's the stress in the x direction plus the stress in the y direction, plus or minus. It was a quadratic equation, so we had 2 solutions. So the maximum principal stress, we took this term and we added this term, and the minimum principal stress, we calculated this term and we subtracted this term. Okay, so there's a plus and a minus in the middle of that because we've got that from a quadratic equation. Sigma x minus sigma y all squared. So our stress is in the x direction, our stress is in the y direction. So these are all direct stresses, sigma. And then we had our shear stress on the end here, plus a half tau xy squared, square root of that lot. Okay, so we know how to calculate our principal stresses from our fundamental direct stresses and shear stresses because of the loading on the component. So what our theories of elastic failure now says is, how do we take that simple one-dimensional problem? We've got that number, that yield stress, that will be published by the material supplier. We've got a simple number for that particular material in that particular load case. How do we take that one-dimensional number, that one-dimensional figure for that material, and apply that to the real world? How do we take that number, work out what our principal stresses are? We know how to do that, and then use those principal stresses to predict when we're likely to see failure. Okay, and it's not an exact science. There are lots of theories out there. The 5 main theories: the maximum principal stress theory, the maximum shear stress theory, maximum principal strain theory, the total strain per unit volume theory, and the shear strain energy per unit volume, or von Mises theory. Okay, so they're the ones that we're likely to come across. Okay, so what we're considering is the failure of the material due to the fact that it is yielding. We're not considering other failure modes such as buckling or fatigue or whatever. What we're considering here is the material yielding and that leading to failure. So up until now, what we've been considering really is the maximum principal stress theory. That is to say, if the stress, maximum principal stress, whether that be sigma 1 or sigma 3, if we're talking about it in compressive terms, but if it's in tensile terms, sigma 1 being our maximum stress, principal stress, if that is greater than the yield stress, if it's equal to the yield stress, that's when we're going to see failure. So we need to make sure that those principal stresses remain below the yield stress of the material. If it's equal to or greater than the yield stress, that's when we're likely to see failure. That's when problems occur. Okay, so that is the maximum principal stress theory, and that's what we've been using up until now. That's been shown to be pretty reliable for brittle materials. However, it should not be used for ductile materials. So actually, when we've been doing our analysis and we've been using that, primarily we've been using that for steels and aluminiums, quite ductile materials. That really isn't the best failure theory to be using. Okay, but that's what we've been using up until now. The maximum principal stress theory, this idea that if our principal stresses exceed the yield stress of the material from this simple one-dimensional tensile test that we've done, we've worked out what the yield stress of the material is. If in our actual scenario, our three-dimensional scenario, if we calculate what those principal stresses are, if they're equal to the yield stress of the material, then we're likely to see failure. So that's the maximum principal stress theory. The second theory is the maximum shear stress theory. Okay, and here you take the principal stresses, sigma 1 being the maximum principal stress, sigma 2 being the minimum principal stress, and you work out the difference between those, so sigma 1 minus sigma 3, and when that's equal to the yield stress, that's when you're likely to see failure. Okay, and that's been shown to be pretty good for ductile materials. Okay, so there's two of our theories, the maximum principal stress theory and the maximum shear stress theory. The next theory is the maximum principal strain theory, and there we've got our principal stresses times through by Poisson's ratio here, and sigma 2 and sigma 3 we're divided through by Young's modulus. So what we're actually looking here is strain. What we're actually looking at here is strain. Strain is stress over Young's modulus in the one direction. So they've got strain in the one direction, strain in the two direction, strain in the three direction. When that's equal to the yield stress divided by the Young's modulus, i.e. the strain at yield, that's when you're likely to see failure. And that's been simplified to that form there. Okay, so there you can see clearly we've multiplied through by Young's modulus on all of those, assuming we've got the same material, constant Young's modulus. We can simplify it to that. So you simply take your maximum principal stress, you subtract your sigma 2 times by Poisson's ratio, and then subtract sigma 3 times by Poisson's ratio. When that's equal to the yield stress, that's when you're likely to see failure. And that's been shown to be pretty good for cast iron. Okay. However, in theory, it is contradicted by tests with plates, with flat plates, I should say, flat plates subjected to two mutually perpendicular loads. So the theory does break down in theory in that scenario, but actually is shown to be pretty good for cast iron materials. Okay, so there's the third failure theory, the maximum principal strain theory. Okay, the fourth theory, the total strain per unit volume, and this here is starting to look, you know, this big long equation here. Essentially, we've got a weighted average of our principal stresses. We've worked out what our principal stresses are, and you can see here they've been squared, multiplied by Poisson's ratio, divided through by Young's modulus. So this essentially is strain, so hence total strain per unit volume. Here you've got the strain per unit volume when that's equal to the Young's modulus, the yield stress divided by two lots of the Young's modulus. So there we've got, so this is something to do with strain associated with the yield stress. When we've got that scenario there, that is when we're likely to see failure. And again, clearly we've multiplied through by 2e. We've multiplied through both sides by 2e, so you end up with this. Okay, so you'll see it written in this form here. You put your principal stress squared, principal stress squared, principal stress squared, minus 2 lots of Poisson's ratio. Here's your principal stresses multiplied together, added together. When that's equal to the yield stress squared, that's when you're likely to see failure. Okay, and that's been shown to be pretty good, but most of the time, actually, that has been superseded by von Mises. Okay, so hence my comment earlier that most FE solvers actually will default to the von Mises failure criteria. So let's have a look at that, the von Mises failure criteria. Here we've got our von Mises failure criteria. Here it is written out in full here. So the shear strain energy per unit volume. Okay, you can see it's a weighted average of our principal stresses when that's equal to the Young's modulus. The yield stress squared divided by 6 times by the shear modulus. That's when we're likely to see failure. And again, you can see that's been simplified. Most of the time, you'll actually see it written in that form there. Okay, so we've got our principal stresses squared, our principal, so sigma 1, sigma 2 squared, sigma 2 minus sigma 3 squared, sigma 3 minus sigma 1 squared. Okay, and that's equal to 2 lots of the yield stress squared. That's when you're likely to see failure. That's widely regarded as the most reliable failure theory, particularly for ductile materials. So hence my comment earlier, most FE solvers will default to showing you the von Mises stress. You can see now why von Mises stress is always positive, because we're taking our principal stresses and we're squaring all of those. See, all of those terms are squared. So clearly you're going to end up with a positive number. Okay, so your von Mises stress is going to be a positive number, and we can compare that to the yield stress of the material. And when we get to this value here, that's when we're likely to see failure. Okay, and like I say, that's widely regarded as the most reliable failure theory, particularly for ductile materials. So if you're dealing with a ductile material, most of the time, in most scenarios, you would be dealing with steels or aluminiums or something like that, pretty ductile materials. It's reasonable actually to use von Mises failure theory because it's been shown to be pretty good for ductile materials. However, if you're dealing with materials which are brittle, ceramics or carbon fibers or something like that, then actually you need to be questioning whether or not using the von Mises failure criteria is actually the correct failure criteria to be using. We've seen a few failure criterias now. Potentially, maybe we should be using this. You can see here before ductile materials, we should be potentially using something like that, the maximum shear stress theory, potentially. I'm not saying that is the right one to use, but potentially there are other more appropriate failure theories which you should be using. Okay, rather than the von Mises stress. So it's very easy when you do some analysis and you see the default values, just to accept the default values and assume that those are correct. But it's important that you understand the theories of what's going on, how those numbers have been calculated, and whether or not they're appropriate. So don't just blindly accept the results, look at them, look at the failure theory, for example, that the FE solver might be using and think, well, is that appropriate for this particular material? Should I be using a different failure theory, for example? So there's a summary of the failure theories which we've been looking at there. Maximum principal stress, maximum shear stress, maximum principal strain, total strain per unit volume, and so on, down to von Mises. The numbers which we need to be considering are here. Okay, so here we can see how we would compare the principal stresses to the yield stress to determine whether or not we're likely to see failure. Okay, so you can see all of these failure theories are simply taking a weighted average of the principal stresses. So taking the principal stresses, doing some calculations with them, squaring them, multiplying them together, taking them away from each other, multiplying them by Poisson's ratio, dividing them by Young's modulus, whatever. We're taking our principal stresses and calculating a number of using those principal stresses and comparing that to the yield stress of the material from this simple one-dimensional tensile test, which we've previously carried out. And then that will tell us whether or not we're likely to see failure. And like I say, it's not an exact science. There are different failure theories out there. However, it gives you a chance to understand whether or not we're likely to see failure based on those values. So what I'll do, I will upload there's a few examples which I want you guys to try, as always. Okay, some examples using the theories of elastic failure. And if we look at this handout here, there are 4 questions. Have a go at those questions. Okay. What I'll also upload are solutions to those questions. So here's the solutions to those questions. I've written them out. Okay, have a go at those as well. Okay, now, like I said in the introduction to this video, there is some prior knowledge which I am assuming which you will need to draw upon to answer these questions. So, for example, if we look at question 1, question 1 says a material subjected to a simple tensile test shows an elastic limit of 240 megapascals. So there we've got this simple one-dimensional test. Okay, calculate the factor of safety provided if the principal stresses set up in a complex 2D stress system are limited to 140 megapascals in tension and 45 megapascals in compression. The appropriate theories of failure which your answer should be based are the maximum shear stress theory and the maximum shear strain theory. Maximum shear strain energy theory. Okay, now I'm not expecting you to remember the formulas, so have a look at this table here and you can pull out the relevant formulas which the question is asking you to use. Okay, as always, I don't expect you to remember formulas. That's not me assessing or understanding how good you are as an engineer. That's just me simply assessing how good you are at remembering formulas, how good your memory is. Okay, in the real world, you don't do that. You ask a colleague, you look it up on the internet, you use Google, you look in a book, whatever. You get the equations from another source and you use those. What is important is that you understand how to use those equations. We have a look at this first question here. That question describes what's going on, and I want you to look at the 2 different failure theories in order to answer that question. When you do that, you will be drawing upon, I will be asking you to draw upon some previous experience. So if we have a quick look at the solution to that question, clearly we are introducing a factor of safety. So the theory here that we're considering, we're taking our principal stresses, we're working out the difference, we're comparing that to the yield stress, and that is telling us when we're likely to see failure. But we've introduced the factor of safety, so actually it's not the difference of those related to the yield stress, it's the difference of those related to the yield stress divided by this factor of safety. There's our factor of safety. That's how we can calculate what our factor of safety is. Okay, you can see there I've got the factor of safety according to that failure criteria. I've then gone on and used the factor of safety according to that, the von Mises failure criteria. Now, clearly, to use these simple theories of elastic failure, they're based on the principal stresses. So the first thing that we're going to need to do in these questions is to understand what the principal stresses are in our stress system which has been set up. Once we can calculate our principal stresses, we can work out the weighted average of those principal stresses depending on whatever failure criteria we're using, and compare that to the yield stress to determine whether or not we're likely to see failure. So question number 2 says we've got a steel tube, mean diameter and thickness 3 mil. Calculate the torque which can be transmitted by the tube with a factor of safety of 2.25 if the failure criteria is the maximum shear stress failure criteria, the maximum shear strain energy criteria, and the maximum shear strain energy criteria. The elastic limit of the steel in tension is 225 megapascals, and Poisson's ratio is 0.3. 3. Okay, so again, we're told what the limit is in stress in this simple one-dimensional test. What we now need to do is to calculate what the principal stresses are and then use these failure criteria and compare the values for the weighted average calculated from those failures, different failure criteria, to this number, which we're told in the question. Okay. In order to do that, the first thing that we're going to have to do is draw upon some of our complex stress theory in order to understand what the principal stresses are. So we use complex stress theory, and actually in this question, not only do we use complex stress theory to calculate those direct stresses, we also need to use the simple theory of elastic torsion in order to understand what those shear stresses are. Okay, so this thing is in bending, it's also carrying a torque, therefore it's in shear as well. So we've got direct stresses set up from our complex stress theory. We've got shear stresses set up from our simple theory of elastic torsion. Okay, so if you're not completely familiar with those, go back and refresh your memory on those two theories. Potentially watch the videos which I have generated discussing those two theories. Okay, so we use complex stress theory and then the simple theory of elastic torsion to work out what our direct stresses and shear stresses are. Okay, we've then gone on, we've used calculated the polar second moment of area of this shape, shear stresses, so we can relate that to the torque. So we've got our shear stress in terms of the torque. Okay, so up until now, we've not used any simple theory of elastic failure. We've simply calculated the direct stresses, the shear stresses and the direct stresses, which are generated by this loading scenario. Okay, we've got the direct stresses, that's equal to the shear stresses. We've calculated what the shear stress is in terms of the torque which is being transmitted. We can then look at the question itself and look at the failure theory which we're asked to understand and calculate, therefore, what shear stress we can calculate. Once we've got our shear stress, we can calculate our torque. Okay, second question, second part of the question, then we've got a different failure criteria, and again we can plug in our direct stresses and our shear stresses, which we've calculated earlier, to work out what torque we can carry. Same for part 3. Part C, we've got yet another failure criteria. Plug in those direct stresses and therefore work out what torque we can carry on our shaft. Question number 3 then. So we've used complex stress theory, we've used simple theory of elastic torsion, simple theory of elastic bending. Okay, that's what we're going to be using in question 3. We've got a mild steel shaft of 50 mm diameter subjected to a bending moment. That should read bending moment of 1.9 kilonewton meters. The yield point of the steel in simple tension is 200 megapascals. So there's the result of our simple tensile test. Find the maximum torque that can also be applied according to the maximum shear stress theory and the shear strain energy theory of yielding. Okay, so we use the simple theory of elastic bending to work out our direct stresses. In order to work out our direct stresses, we're going to need to calculate the second moment of area, the circular shaft. So there's a second moment of area of our shaft. So therefore, we can use simple theory of elastic bending to work out what those direct stresses are. We're also using the simple theory of elastic torsion to work out what the shear stresses are. We can then go on and use complex stress theory to work out, therefore, what our principal stresses are in terms of those. Got our principal stresses. Once we've got our principal stresses, we can then look at the failure criteria that we're asked to use. So, for example, our failure criteria might be this. So we calculate our failure criteria and therefore the torque which this shaft can use. So in this question, we're using the simple theory of elastic bending in order to calculate the principal stresses. And then the final question, question number 4, we're using a thin-walled steel cylinder. So we're going to use thin-walled cylinder theory. Thin cylinder theory. 2 meters diameter subjected to an internal pressure using a factor of safety of 2 and a yield stress in simple tension of 400 megapascals. So there's our simple tensile test for this particular material. Calculate the wall thickness on the basis of the Tresca and von Mises yield criteria. Maybe assume that radial stresses in the wall are negligible. Okay, so that last sentence there means that we can use thin cylinder theory if we couldn't assume that the radial stresses were negligible. If they change over the thickness of the wall, we would need to use thick-walled cylinder theory. Okay, but according to this question, we can use thin cylinder theory. So we know from thin cylinder theory, we've got hoop stresses, longitudinal stresses, and radial stresses. So if you're not familiar with all of those, if you can't remember those, hoop stresses, PD over 2T, longitudinal stresses, PD over 4T, calculate those. Our hoop stresses are a maximum, so therefore they're sigma 1. Our longitudinal stresses are a minimum. Our longitudinal stresses are less than that. So our longitudinal stress is PD over 40. Clearly, that's half of that. So there's our maximum. Sigma 2 is half of that. And then our radial stresses we've assumed is negligible. Okay, so we're using thin cylinder theory to calculate those principal stresses. Once we've got those principal stresses, simply a case of plugging those into the equations which we're asked to use in order to work out the answer to this question. Okay, so according to the first failure criteria, the thickness of the cylinder needs to be 12.5 mil. According to the second criteria, actually it can be a little bit thinner. It's a little bit more optimistic. It's saying the thickness actually only needs to be 10.8 mil. Okay, so have a look at those questions. So like I say, those questions, they draw upon some previous knowledge in terms of some theory of elastic torsion, some theory of elastic bending, thin cylinder theory, complex stress theory. You're going to use all of those to work out what your principal stresses are. Once you've got your principal stresses, you can apply those to what we've learned today. So you just calculate a weighted average of those using those formulas from that table. Calculate those, compare those to the yield stress of the material, and that tells us whether or not we're likely to see failure. Okay. So have a look at those, try those questions. We'll go through those in class. We can discuss the theory and any queries which you've got about any of those examples that you've gone through. Okay. Until next time, I'll see you then. Cheers. Bye-bye.